Thank you very much, Professor Prashant, for accepting our invitation. So, as you know, and everybody knows that it is 75 years of our independence, and the government of India is on the drive of this Azadi Ka Amrit Mahotsav. So, we thought that I think it is good time to appreciate the great scientists we have in the last century. So, we started this series, and you are the first speaker under this colloquium series. So let me introduce about the department. The physics department came into existence in 1964 when BITS Pilani also came into existence. It existed even before 1964 as a part of Birla College of Science. And at present, we have 20 faculty members who work in different areas of physics, almost all areas of major areas of physics, starting from cosmology, early universe, nuclear and particle physics, and atomic and molecular physics, condensed matter physics, biophysics, complex systems, and so on. So each faculty member has a different research area. So we are fortunate that we have the group members having different type of research areas. So at present, the department is supported by this DST FISH funding. And in last 5 years, we have completed or either completed or ongoing 25 individual projects. And we are publishing very high quality papers in last, especially in last 5 to 6 years. And we offer this MSc Physics program, which is integrated MSc Physics program. And apart from MSc Physics program, we have PhD program. And for engineering student, we offer this minor in physics program also. And the physics department is a university. We have two different campuses, one in Goa and one in Hyderabad, where physics department is also there. So collectively, all three departments recognized by the QS ranking internationally and nationally. And at national level, we are at 16th place. So with this, I stop about briefing about the department. So let me introduce the speaker. Professor Prashant Shukla is working in NPD BARC as Scientific Officer H and is professor at Homi Bhabha National Institute. After graduating from Vikram University, Ujjain, he joined 36th batch of training school in 1992. From 93 onwards, he has been working at various energies in nuclear physics, guided 9 PhD students, and got 1,400 publications. He worked at the University of Heidelberg during 2004 and 6. A large fraction of time he has worked in international experiments like CMS and Alice at LSC, Phoenix at BNL, INO collaboration, and COSI-GEM in Germany. He has also worked on phenomenological interpretation of nuclear collisions, quark-gluon plasma, and neutrino physics. In recent years, he invested in cosmic particle interaction in the atmosphere and at the Earth. He has also been working on quantum device simulations and fabrications. So now I invite Professor Prashant Shukla to take over the stage. Over to Professor Prashant Shukla.
Thank you, Professor Chobisa. Let me just try sharing the slides.
Yeah, it is there.
Yes, yes.
Yeah.
1 minute. So it is visible full?
Yes, yes, yes.
Okay.
Yes. I request all others to mute yourself. Mute your microscope other than Professor Prashant. Microphone, please.
Yeah, now it is visible full?
Yes.
Okay, so let me thank again Professor Chobisa and Physics Department of BITS Pilani for inviting me on this online lecture series. And really, I am very fortunate to give the talk on such a great personality, Dr. Homi Jehangir Bhabha. I also thank Professor Madhukar Mishra for introducing me to the department uh, and making way for this online colloquium. So I would start with this quote of Professor Bhabha. It's a life of Homi Bhabha. So here I read it, and it's very inspiring quote for me, and I'm sure it will be inspiring for all of us. I know quite clearly what I want out of life. Life and my emotions are the only things I'm conscious of. I love the consciousness of life, and I want as much of it as I can get. But the span of one's life is limited. What comes after death, no one knows, nor do I care. Since, therefore, I cannot increase the content of my life by increasing its duration, I will increase it by its intensity. Art, music, poetry, and everything else that I do have this one purpose, increasing the intensity of my consciousness of life. Homi Bhabha. So, with this inspiring quote, I move to the next slide. Homi Bhabha has been a multidimensional personality. You can call him great scientist, a great theorist, a great technologist, father of Indian nuclear program, founding pillar of Indian science, Bhabha a painter, Bhabha a musician, Bhabha a poet. So when Professor Chobisa asked me the title, it was very difficult for me to decide the title. In fact, this portrait you are seeing on this slide is made by Professor Bhabha himself. So you can see. So this I have taken from TIFR archive, which he has made at the age of 17 years. So preparing this talk was a pleasure for me. I will describe Bhabha's scientific journey and events in his life in chronological order. I will supplement it with physics concepts connected to the work, as I know I'm delivering this talk to a physics audience, mostly physics students of MSc, PhD, and the teachers. So I'm sure the students and teacher will find the talk inspiring and interesting. This is the beautiful family of Homi Bhabha. Homi Bhabha was born on 30th October 1909 in Bangalore. You can see his parents and parent Jehangir Bhabha and mother Mehrabai. Yeah, this is Homi Bhabha as a child. He has a younger brother whose name is Jamshed. His father actually was a lawyer in the state of Mysore, and their education was a very big tradition in their family, and mm, even their grandparents were educationalists. Early education of Homi Bhabha happened in Mumbai. So from Bangalore, the family moved to Mumbai. So this you can see here, the bungalow where Homi Bhabha mostly spent his childhood and young age. He studied in Elphinstone College and Royal Institute of Science in Mumbai. His aunt was married to Dorabji Tata. Dorabji Tata was second chairman of Tata Group, the famous company of the Tata Steel and Tata Steel, which was established by his father. So you can see that this Bhabha family and this Tata family had relations. In 1927, Bhabha went to Cambridge. So that was called Gonville and Cowes College. He was sent there to study mechanical science. The intention of his family was that they wanted him to join Tata Iron and Steel Company. But Bhaba's mood was not in really in mechanical science, but in the physics. In 1928, he wrote to his father, "Physics is my line. Each man can do best and excel in only that thing of which he is passionately fond, in which he believes, as I do, that he has ability to do it, that he is in fact born and destined to do it. I am burning with a desire to do physics." So you can understand the his burning of the desire to do physics, and you can really see what was the physics scenario during that time. So the physics scenario leading to 1932, the atomic model was taking final shape, and all the particles, electrons, protons, and neutrons were discovered. Neutron was discovered in 1932, and the model was physically in place that protons and neutrons reside in nuclear, and the electron is surrounding us. It looks so complete. You can make all materials with the three particles. Whatever elements, whatever compounds you can make with these three particles. But really, it was much more incomplete because the nuclear force which was binding protons and neutrons together was not well understood. Protons we know are the positively charged particle, and neutrons are the neutral particle. And this nuclear force collectively keeps them together. So this was one problem. Another problem was, radioactivity and this beta decay spectrum, which was coming from the many of these unstable radioactive nuclei. So this is where the attention of physicists was during that time. And uh, if you see this particle and nuclear physics development during 1927 to 1940, James Chadwick, as I told, he had discovered neutron. He was in Cambridge that time when Bhabha was there. Dirac was in Cambridge that time. This picture you can see with Pauli, Bohr and Fermi here, and PMS Blackett. I will tell later what this guy did. Chadwick had discovered neutron. Dirac had proposed antiparticle at Cambridge. Fermi proposed a new particle, neutrino, in beta decay in 1934. Half-spin particle fermion was formulated by Pauli and Fermi. So you can see that all these activities was concentrated in and around Cambridge and in Europe that time. And many of these great scientists whom we learned about in textbook were active during this period from 1927 to 1940. Another important thing which I wanted to tell is Fermi worked on nuclear fission with slow neutron in 1934, and many other like Otto Hahn and all followed that work. Bohr proposed model for nuclear fission in 1939. So about nuclear fission and with the neutrons, I will come little bit later. Just for the completeness in this scenario, I will just review this cosmic ray field. During 1930 to 1940, it was a most exciting era. So what are these cosmic rays? These are the primary cosmic rays, charged particles like protons and helium nuclei. They are accelerated to enormous energies somewhere in the cosmos, the processes like supernova, AGN, etc. Whenever these particles enter the Earth's atmosphere, they create two kinds of they create particle shower, which you can divide into two kinds. One is electromagnetic shower and one is hadronic shower. So this is more penetrating part of component. So here I will little bit explain about this figure. So let's see a proton falls on the atmosphere, and then it will interact with the nitrogen and oxygen. It will create lot of neutrons, protons, and this strongly interacting particle like pi plus, pi minus, and pi zero. Pi zero can decay to two photons, and these photons can again create electrons. Like that, there's a shower which we call electromagnetic shower. This why I'm explaining, because this is one of the area, this is one of the thing, the theoretical process which Bhabha gave the theory for. Another part is this more penetrating part, hadronic part. So pi plus pi minus can decay to mu plus and mu minus and a neutrino, which reach to the earth, and many of these particles like neutrino, they pass through the earth completely. So these are these particles which are falling on the earth's surface and passing through us all the time. And this was most of these particles were discovered in this era. So why I'm explaining this, because this was the time in Europe and in Cambridge that these some of the most fundamental aspects in particle and cosmic ray physics were getting developed. Uh, Further, I will just list some more things. There have been many discoveries associated with the cosmic rays. Some of them I will list here. As I told, that Anderson discovered positron as an antimatter using magnetized cloud chamber from cosmic rays. PMS Blackett and Oceani demonstrated electromagnetic shower in 1933. In 1936, Anderson found a medium mass charged particle using magnetized cloud chamber with lead sheet. Using range and curvature, it was concluded it is much heavier than electron but lighter than proton. Bhabha, along with Kramer and Pierce, were responsible for the nomenclature of this particle meson. It was confused as Yukawa meson, carrier of nuclear force, but later this was named as muon. As I told you about the electromagnetic shower developed in the cosmic ray, in 1937, Bhabha and Hitler gave theory of electromagnetic part of cosmic ray shower. Basically, a high energy electron, when it passes through a medium like air, it gives a photon due to Bremsstrahlung. These photons can further give electron and positron pair. This electron positron pair can further travel, and each of them can give photon. There is as this particle propagate in the medium, there's a bigger and bigger shower getting produced, and more they travel, then after some time they will start reducing. So Bhabha actually gave the number of these particles as a function of depth and energy, and this was known as Bhabha and Hitler theory. I'm giving the photo of his collaborator also here, Hitler. In the same time, Carlson and Oppenheimer also worked on it. So just to mention that. So this was one of the biggest particle physics contribution of Bhabha. Here I summarize Bhabha's contribution in cosmic and particle physics. 1937, Bhabha and Hitler gave theory of electromagnetic part of cosmic ray, which I just explained. He also, to explain the penetrating component, he proposed there must be an intermediate particle with same characteristic as electron but 200 times heavier. It is called meson. Now we know that it's a muon, and it is exactly 200 times heavier than mass of electron, which Bhabha had predicted that time. Bhabha was first to point out that since cosmic rays are moving at almost with the speed of light, they are the best place to verify Einstein's special theory of relativity. Like time dilation. So whenever an object traveling with a velocity near to speed of light, the time where what we observe, it gets delayed, and that was really measured in during cosmic rays. We know that the lifetimes of meson increases more than 20 times. Otherwise, they would not have been able to reach to the Earth, and could have decayed before that. But we see a lot of particles falling on the Earth with which actually had very small lifetime. The another important theory which Bhabha gave, and this is called Bhabha scattering. This Bhabha derived a scattering cross section for electron and positron. In the quantum electrodynamics, which was developed by Dirac, it is said that the electron and positron exchange a photon, and that's how this Coulombic interaction gets developed between the two charged particles. Bhabha gave another term for this scattering. He said that this electron and positron can get annihilated and can give a photon, which this photon can again create an electron and positron pair. So this term was added to the scattering, and this is very elegant expression for this scattering cross section in terms of just these three variables A, S, T, and U, which you can construct using the momentum of the initial and the final particle. This formula is so accurate that it is routinely used as luminosity monitor in E plus E minus collider all around the world. Now let me come. So when the World War broke out in 1939, during that time Bhabha was in India for a short vacation, and then after that he did not return to Europe. Bhabha joined Indian Institute of Science in Bangalore. It was headed by Professor C.V. Raman, and he established a cosmic ray lab there. He continued working on Bhabha-Cormon equation. In 1941, he was elected fellow of Royal Society and got Adams Prize. Here, this is a picture of Indian Institute of Science, and here you can see Bhabha sitting with Professor C.V. Raman and Dr. Vikram Sarabhai. Bhabha, while living in India, Bhabha realized that there's a big difference between his Cambridge days and his days in India, and he felt that there is a need of good institutes in India. So he proposed a new institute in Bombay, which could cater to both the fundamental physics and practical applications in industry. He planned that the new institute would conduct research in nuclear energy as well. Such a proposal was sent to Sir Dorabji Tata Trust in 1944. JRD Tata was the chairman of Tata Group that time, and Dr. Bhabha in his letter wrote, most of the great advances in science and therefore in industry have had their origins in fundamental research, without which they would have been impossible or would have been long delayed. It was a big letter, but I'm just quoting some of the most important sentences from that letter, which and the letter really worked. The Tata Institute of Fundamental Research was opened in December 1945. In the beginning, it was run in old yacht club in Bombay. The new building was sanctioned at a plot in Kolaba, which was selected by Bhabha himself, and this started in the new building started in 1954. Here you can see the model of this TIFR building, along with Pandit Jawaharlal Nehru, our first Prime Minister, and Bhabha explaining to him. And this place was actually a picturesque place. The one side is the beautiful sea, and the other side is a very green place where this institute is placed. Today, the main funding of TIFR comes from Department of Atomic Energy, although in the beginning, the Tata Group gave the seed fund for this institute. Bhabha continued to do his cosmic research in India, in Bangalore and in the TIFR Mumbai during this period 1948 to 58. Many of his colleagues got inspired by him. In fact, these balloon flights for cosmic ray research, these were started by Bhabha himself. These balloons were made of plastic mixed with carbon powder. There's a lot of experiments were done to avoid, because whenever this normal plastic balloon are sent to up in the sky, some 20 30 kilometers, there is a because of the small temperature, this plastic got frozen actually. So this carbon powder was mixed in that, so that that they absorb heat from the sun and keep warm. But if you mix a little bit more carbon powder, then this plastic also start getting melted. So that's why there's a lot of experiments were done to avoid this freezing and melting of these balloons. But finally, these balloon flights were successful. It was done in Bangalore and Delhi and you can see here a plot which is as a function of pressure in millibars. So as you move up in the sky, the pressure starts decreasing, and the intensity of the intensity or the counts of the counters which are placed in the balloon flight, they see more and more current in them. So you can yes, so these with these because he did the experiment in four conditions. One was at Bangalore and one was at Delhi, which are at different altitude, and also with and without lead to have cosmic rays, for the both penetrating and the electromagnetic component. So this paper actually concluded that the flux increases with latitude and altitude, and it was published in Physical Review 1953, and this was what was in India. This is one of the research. There have been many research work, but I cannot complete the talk otherwise. So I would just switch over to this another important topic, which is called the nuclear fission energy. So I will just explain a little bit basics of this, because the next part of my talk will use lot of terminology from this nuclear fission. But you are physics students, so this is just a very brief review for you people. So when a heavy nucleus is bombarded with neutrons, it breaks into two medium mass nuclei, releasing enormous energy. So 2 to 3 neutrons are released in the reaction, which could further cause fission. So it means that a self-sustained chain reaction is possible. So here I am showing one uranium nucleus. It is bombarded with a neutron, and then it causes fission. Two fission fragments flying in the two directions, and 2 to 3 neutrons are produced. These neutrons can cause further fission of the neighboring nuclei, and then 2 to 3 more neutrons are produced. So here in this, if I count the number of fission increasing exponentially. So in the first generation in the first generation 3, and then 9 and 27 at even. So it's releasing enormous energy, causing big explosion, and this is used in the nuclear explosion or the atom bomb, which was put in Hiroshima and Nagasaki soon in somewhere in 1945. But one could tap the energy for peaceful purchase if you can control these neutrons. So what can be done if only out of these 3 neutrons, only 1 neutron from each generation causes fission, then we call it a k equal to 1 or criticality condition. So this I will use. So basically, there is only 1 neutron from each generation causes further fission. So the chain continues, but it remains under control. So this is called. So whenever a reactor achieves this condition, it is called critical condition. We define it by k equal to 1. If k equal greater than 1, then it can go to nuclear explosion. If k is less than 1, then it is a subcritical condition. So soon Bhabha started looking for establishment which could cater to this atomic energy research, and atomic energy establishment AEET was conceptualized in Trombay. Now we know that this is institution known as BARC. There is also a very good place which was again found by Dr. Bhabha. There's a hill at one side, and there's a sea at other side, and there's a full institution which was built at that time. There have been many atomic energy setups formed. A host of organizations were formed, within just 10 years of our independence. So Tata Institute of Fundamental Research 1945, Atomic Energy Commission was formed in 1948, Raw Material Division, because you want to explore these uraniums and minerals from the excavate from the mine. It was formed in 1949. Indian Rare Earths Limited 1950. Department of Atomic Energy formally was formed in 1954. Atomic Energy Establishment started operating from 1957. So these were the first reactor, Apsara, which is called Apsara reactor, and it became critical in 1957. The nuclear progress was very fast under Bhabha's leadership. So Asia's first reactor, Apsara, it was 1 megawatt, was operational in 1957. You can see the building from outside, and here you can see Pandit Nehru seeing in the reactor. Actually, this was a swimming pool type of reactor where you put this enriched uranium core in water. So water acts both as a coolant and as a moderator. And you can see nice blue Cherenkov light, and that's where Pandit Nehru. Although this is a black and white picture, so you can't see a blue light here, but he might be seeing that blue light at that time. This was a big news in India and in the world that time, that within 10 years of independence, we could get the first nuclear reactor, and this famous cartoon by R.K. Lakshman depicting Pandit Nehru driving this common man, and this bullock cart, and the wheels were replaced with the nuclear wheel. So this was published in on the eve of the dedication of the first nuclear research reactor, Apsara, in 1957. But soon there were bigger reactors like Cyrus reactor, which are pressurized heavy water reactors were started getting constructed. The Cyrus reactor was under construction. You can see the picture here, under construction from 1954 to 1960. It's a 40 megawatt reactor, which was built with the collaboration with Canada, and it's known as Canada-India Reactor Utility Service. So it is mainly used for research and producing radioisotopes. It runs with natural uranium. So that is the most important thing, that this natural uranium was produced in India itself. And then so this is at right side. If you see, I have just put one schematic of this pressurized heavy water reactor. You can see these are the fuel rods, which are made of natural uranium, and they are immersed in heavy water, which is used as a moderator and as a coolant. Coolant means whatever extra energy it takes, it gets circulated outside. A moderator means it slows down these fast neutrons to thermal neutrons, which can cause further fission. There are also control rods. Any eventuality, the control rod automatically come down and absorb the extra neutrons, and the reaction stops. The cooling cycle is always like that. There is cooling is done in closed cycle. There is a inner primary cooling which is done with heavy water, and then there is a secondary cooling which is done with seawater in this case. So this primary cooling and secondary cooling, they are never get mixed up, because of if they are mixed up, then there is a radioactivity this thing. So they are closed loop cycle for primary and the closed loop cycle for the secondary. In this case, because this is a research reactor, so power is not consumed. So whatever extra heat it is disposed in the sea. But in power reactor, whatever steam you generate is used for the for operating turbine, and you can generate electricity. So this is Bhabha and our second Prime Minister Lal Bahadur Shastri at Cyrus reactor in 1964. I think Bhabha must be explaining this these cooling cycles and the control systems of the reactor. Nuclear strategy. Bhabha formulated three-stage nuclear program for India. So first stage was the pressurized heavy water reactor PHWR, which runs on natural uranium. This has a fuel. The natural uranium is a mixture of uranium-235 and uranium-238. Uranium-235 is used as fuel, and the advantage is that whatever uranium-235 is there gets converted into plutonium-239. So in the second stage of our nuclear program is called fast breeder reactor, where you can use this uranium-239 plutonium, which was produced in the first stage as a fuel, and then you can mix it with thorium-232, which can get converted to uranium-233. This is what Bhabha has formalized, because this thorium-232 has a vast there's a vast stock of this material in India, and if you can convert this thorium to uranium-233, which is a fissile material, then in the third stage, advanced thermal and fast breeder reactor, we can use this uranium-233 as fuel, and this will ensure our this energy security of India, because there is a lot of scope, means lot of stock for the thorium-233, 232. So this was formalized long back by Bhabha, and India continued with this strategy. So this is AEET full plan, which Dr. Bhabha is explaining to Lal Bahadur Shastri. This is as a modular lab. There is this Cyrus reactor, and then there are 6 halls, experimental halls for different purposes. There is a big workshop. There is a central complex with auditorium. There is a processing and analyzing this nuclear fuel here. So this plan was in full swing, and here you can see Bhabha himself was monitoring the construction of various facilities inside the BRC, and you can see this already this 6 hall which was there in the here in the next slide. So you can see that, and this coming up was this modular lab at this place. Now I would come to the sad part of the talk. Unfortunately, Bhabha died untimely, and on 24 January 1966, when Air India plane going to Geneva, it crashed over Mont Blanc, which is a mountain range over France. In fact, Lal Bahadur Shastri had died just 13 days before in the same month. So this January 1966 was a very terrible month for India, and this is the news item in the newspaper where they said Bhabha among 117 dead in air disaster, and Air India Boeing crashes in Mont Blanc area, and wreckage was found by some helicopter pilot. Around same time, Indira Gandhi took over as Prime Minister, and you can see the photo, the news on the same day. So this is the Alp range in Europe. You can see the somewhere in the France, Switzerland, and Italy, and here you can see the picture of those mountains. There was a big condolence at AEET, which is BRC now, and you can see our scientists and the workforce gathered for this condolence, and you can see it was addressed by the next senior people from this place, and you can see the construction was still. You can see there's a building called Modlab, and the construction is still going on about the roads and lawns. What you can see is Bhabha Atomic Research Centre. So Atomic Energy Establishment was named as Bhabha Atomic Research Centre post death of Dr. Bhabha, and you can see the BRC how it looks at present is the Cyrus reactor. There's a Dhruva reactor which I will come back to it, and this is what is the mod lab. Which and the place where I showed the condolence meeting was this place. In terms of Bhabha's word, again I will quote: a scientific institution, be it a laboratory or an academy, has to be grown with a great care like a tree. And really, it was taken a great care like a tree, and it's a full blown up tree now. Uh, India could further progress on its nuclear program, and in 1974 it did a Pokhran blast. It did a nuclear device test at Pokhran. India termed it as a peaceful nuclear explosion. And after that, the many of these the collaboration with the Canada, France, and US, they were stopped, and we could make a new reactor which is called Dhruva reactor much later, after 12 years. So this became critical in 1986. So here this is Cyrus reactor, and this is Dhruva reactor, which is 100 megawatt thermal pressurized heavy water reactor. Both Cyrus and Dhruva were used for neutron beam research and isotope production. Just 10 years back, the Cyrus reactor has been shut down permanently due to aging, because here it had already spent some 50 years of operation. So at present, the Dhruva reactor is operating in its full capacity and producing isotopes for medical and industrial purposes. There's also a big institute just like BRC in Kalpakkam, which is called Indira Gandhi Centre for Atomic Research (IGCAR), and there's a 40 megawatt fast breeder reactor became operational in 1985. So this was our entry into the second stage, which was formulated by Bhabha. Earlier, it was not in the beginning only with very low energy. It was stopped, but later this energy was subsequently increased about this reactor. India also did thermonuclear explosion on 11th and 13th May 1998. So there were 5 explosions conducted, which included a thermonuclear device which had the power of 45 kiloton. I have not touched the power reactors. There have been numerous power reactors operating at various places. This is a picture of Rajasthan Atomic Power Station, which is also a pressurized heavy water reactor, which was designed during Bhabha's time. So this is one picture. This is a map of all atomic energy establishments in India. This includes nuclear research reactors, power reactors, heavy water board, minerals board, waste management, and many other facilities. So you can see they're all spread all over India, and this is what the nuclear map of India looks at present. Some of the things which I could not touch upon, that Bhabha is an artist. So Bhabha was living proof that scientific excellence can go with excellence in arts. So here I'm showing one picture which also I took from this TIFR archive. Bhabha with the collection of his own paintings. So all his paintings were placed in his house, and this is a picture with that. So with that, I should come to the end of this talk. And Homi J. Bhabha, 1909 to 1966. I will again quote with the same line which I started with. I cannot increase the content of my life by increasing its duration. I will increase it by its intensity. Bhabha died at the age of 56. At the time of his death, Bhabha was living a full and accomplished life. He had established TIFR, BRC, DAE, and established nuclear India on world map. So thanks all. And these are here I'm listing some sources from where I took the material. Thanks again.
Thank you very much, Professor Prashant Shukla, for this wonderful and enlightening talk about the life and work of Dr. Bhabha. So now we can take few questions if audience wants to ask from the expert, from the speaker, sorry.
Yeah, I'll be happy to answer some questions.
Yes, so you just raise your hand and I will coordinate the question answer session. Yeah, Amol. Yeah.
Hello.
Yeah, Professor Amol. Yeah.
Am I audible?
Yes.
Yeah. Okay. Yeah. So very nice talk, Dr. Prashant. So my question is like, what about this NPCL? So when exactly this came into picture, like National Nuclear Power Corporation Limited?
So this nuclear, which is called Nuclear Power Corporation of India Limited, NPCIL.
Yeah.
This is part of Department of Atomic Energy. So earlier it was part of BRC itself, whatever this institution. But later on, because of the commercializing the operation, it was made as a corporation, and it is primary responsibility is to construct and run the nuclear reactors which are providing nuclear power, like you have one at this Rawat. So these are run by NPCIL.
Okay. So actually, I have done my PhD in BRC only under Dr. N.K. Gupta of Theoretical Physics Division that time.
Oh, right.
Thank you.
Dr. Kamlesh Kumar.
Shukla ji, actually just I had one inquiry from the Fermi telescope data analysis. We know that you have the cosmic ray origin either from sun or like your this other places in the universe due to supernova explosion. But then why is it different? I mean, why at the origin of the cosmic ray generation, why it is different? Because we know that it is different. I mean, whatever particle details we get from the cosmic ray received at the Fermi telescope from the sun or from supernova explosion, but then why is it different?
Why is it different?
I mean, why it is different? The generation mechanism should be same. Why it is different?
No.
Why
Actually,
different
the
data comes?
mechanism, it all depends on the energy scale. For example, suppose there is a supernova explosion. Now their energy scale is very high there. This active galactic nuclei. There is the energy of the cosmic rays from these cosmic sources, extragalactic sources. The energy is extremely high. Because they're in the active galactic nuclei, for example, there is a there is a there is a charged particles which are moving and generating a magnetic and electric field, and in that high magnetic and electric field these particles get accelerated to enormous energy, and they reach it. In the sun, we know that sun has a lot of energy, but the energy at AGN or in the supernova, that's much higher than the energy of the sun. So the cosmic rays, the charged particles which are coming from sun, are not of that high energy.
So because energy level is higher, and so that means, but then then whatever LHC we have, all the energy spectrum from the sun part, then it should be able to capture. Can whatever is what is the highest energy level which has been detected in the Fermi telescope? Highest energy which they have detected, and then that can be simulated in LHC.
These telescopes and there are many telescopes are operating in the satellites and in the at the high altitudes at the Earth, and people have observed many petabyte many peta electron volt energy. So that is something like 10 to the power 15 of electron volts. So few of 10 to the power 15 electron volts. So that much of energy particles have been observed. Of course, the flux, as you go to the higher energy, the flux reduces exponentially with the power law.
Okay, so more or less due to the energy variation, right? I mean,
Yes.
because beyond this point, the research part is almost same for everybody. It's a bit of sharing.
See, the cosmic
always
particles,
helps.
cosmic
Okay.
particles
Thank you.
which are coming to the atmosphere, they are the charged particles, which is called protons or helium. Now this is the energy spectrum. The energy, which part of energy spectrum is coming from which process or from which part of the cosmos, it makes them slightly different.
Yeah, because fortunately, we have a vacuum throughout, so as such, media is the same. So media effect is automatically taken. So it's like only energy variation at the two origin places, but beyond that, the vacuum throughout vacuum till Earth's atmosphere.
Yeah,
so there won't be any effect.
One thing I will add here: there is a vacuum in the space, but there is a magnetic field. So we know that Earth has magnetic field. So Sun solar system has its own magnetic field. Galaxies have their magnetic field, and these are charged particles. So these charged particles, although they are traveling in a vacuum before they are interacting with the atmosphere, they are all traveling in vacuum, but there's a lot of effect on them due to the magnetic field, and so they change their direction. So that's one thing I will like to add. Okay.
Okay, so maybe Kamlesh. Yeah.
We can have some questions from students.
Yeah.
Only that much time is justified.
Yes. Okay, anybody else?
Okay, thanks, Prashant, Dr. Prashant, for nice talk. Very energetic, enthusiastic talk.
Thank you.
So, thank you very much, Professor Prashant, again for a wonderful talk. And we came to know a lot of things about Dr. Bhabha and his contribution not only in science but in the nation building, in the other parts of life like painter Bhabha and musician Bhabha and so on. So thank you very much, and we will be happy to receive you offline in BITS Pilani if you are in Delhi. So in that case, you can call us, so we can arrange a taxi and you can stay here, and you can give a talk of your research interest also in BITS Pilani. So whenever you have a time, you can call us.
Okay, that's nice. Thanks for the invitation.
And okay. So with this, I think we should close this seminar because we are running out of time. So once again, thank you very much, Professor Prashant, for your time.
So, Professor Prashant, I will meet you during the conference.
Yes. Okay. So let's make it there.
Professor Prashant, if you allow, we can put this recorded lecture on our physics department YouTube channel.
Okay.
You allow us?
Yes.
Okay. Thank you. Okay. So with this, we can log out.
Okay, then bye-bye.
So thanks.
Okay, thanks once again.
Rubisa and Professor Mishra, and thanks all the audience.
Yeah,
Okay,
thank you.
Okay, bye-bye.